Exchange. So I don't think we'll be using the VM today. Should just be a lecture kind of a day. All right, so it's recording now. Okay. Give me a sec, my Zoom crashed. It says it's still recording. What? Huh?
I thought the screen turned off.
Yeah, no, I don't know. It's weird. It's my laptop, I think. All right. So hopefully no problems. It should be recording, I think. So I'll just start kind of going over some ideas, as you guys know, and then we'll get into the main concepts. So remember, all of this, we always want to think in terms of the pillars, right, of information assurance. So the idea here is actually asymmetric encryption is going to help us with confidentiality because we're going to be sending the key. So that's the main advantage. And then also a little bit of authentication as we start looking. I think we kind of hinted at this before, but this becomes really important. And we do it with RSA. So certificate authorities, digital signatures, et cetera, are very relevant to that pillar of authentication. And that's all done through asymmetric and RSA. So again, we'll be using Bob and Alice for some of the descriptions. All right, so as you know, we'll start with the limitations of symmetric secret key encryption. So if you remember, this was we had started discussing this. So the fundamental limitation of symmetric secret key encryption is how do two parties agree on a key, right? So that was the main issue. In order for Alice and Bob to communicate securely, they need to agree on a secret key. In order to agree on a secret key, they need to be able to communicate securely, right? So that's the problem that we can't solve. So this problem is especially common in the digital age. We constantly end up in websites with whom we decide we want to communicate securely, but with whom there is not really an option to communicate offline, right? So basically your solution was always just to email your friend or your partner the key, right? And so, but you can't just email Amazon or your bank a key, right? So how are you going to do that? So that's basically what asymmetric encryption does for you. As I said, when we look at the applications, you'll basically look at creating a website, like it's going to be a web server and a web client through the browser, and then hopefully you'll understand how that works. Okay. So, so as you know, in asymmetric public key cryptography, both communicating parties, Alice and Bob, have two keys of their own. So this is, as I said, before when you were doing these lab assignments, you only had the one key. Now everyone, all of you are going to have your own public and private key, right? And so it's going to become harder because you're going to have a whole bunch of other files now involved in the process. And so again, I mean, you have to do this with a partner to understand this well. Also, I should say, additionally to the scavenger hunt, there is one assignment, the PyCrypto Dome assignment, which I require you to demo, okay? Because it's the only way for me to actually really understand, that you're doing this correctly, right? So that one involves, to get the grade, you demoing things, okay? So it's going to be like the problems, and I'll just say, okay, achieve confidentiality, now integrity, now authentication, with this and that, exchange the key securely, and so on. Okay, so we'll do that at some point. But just be aware where you see PyCrypto Dome, that's the one where you have to demo because I bring in everything together into that one. Okay, all right. But it's a lab. It's basically just a lab. So have two keys of their own. So just to be clear, that's 4 keys total, right? So each party has their own public key, which they share with the world, and their own private key, which they keep secret. All right. One common thing I always see that's common mistake students make is whenever they're running the code, they always run the keys again. And so they're regenerating the keys, but the problem is they've already shared like the public key. So when they run the code and they regenerate the keys, what happens? Now you're using a different set of keys. So obviously you will not be able to decrypt things with the old public key, right? So be aware of that. You only need to run the generate keys function once, right? Then exchange your public keys and that's it. Okay. But it's a common error that I see. All right, so the magic of public key cryptography is that a message encrypted with the public key can only be decrypted with the private key. And this, by magic, I mean math, right? So this is done through math. We're not going to go over there's a lot of theorems, right? That people say, oh, this works because of this and this works because of that. So they've tested these algorithms in terms of the math, but they also test them like they really try to break them. All right, as you know, there's like government agencies that do this, right? They try to break AES, they try to find vulnerabilities in it, or they try to break RSA, and they, as far as the public knows, right, none of these have been broken, right? So that you can, but apparently quantum computers may break them in the future, so there is that issue, possibility. But so far they haven't been broken. All right, so I will show you today how, some of the ideas, or today, in this module, some of the ideas of how you could break RSA, which is an interesting topic. Okay. So Alice will encrypt her message with Bob's public key, and even though Zelda knows she used Bob's public key, and even though Zelda knows Bob's public key herself, she is unable to decrypt the message. Okay. Only Bob, using his secret key, which in this should say private key, should make a note of that, can decrypt the message, assuming he's kept it secret. So there it just means he's keeping something secret, which is actually the private key. Okay. So I think this is where we kind of left off when I kind of went over this idea. And so we'll start here, and then, the rest we'll elaborate. So basically we got Alice and Bob. So it's going to be you guys working together. You'll generate your private and public key. You'll generate those as files, right? Now we can generate private and public keys with Scratch Python, with OpenSSL, with PyCryptoDome, which is a library. So we'll have like 3 ways of generating these public and private keys, okay? But in general, my recommendation is save them to a file, okay? And that's probably the best thing. So that way you can exchange them, so usually create your public and put your name on it, right? And then create your private and put your name on it. You should never email or send the private key, okay? Very important. All right, so basically how it works is you take the plain text and then you're going to encrypt it using the RSA algorithm. So we'll go over some of those details today. We will grab Bob's public key, right, and generate the ciphertext. You send it over an insecure channel. Zelda tries to snoop, but she is unable. And then you get the ciphertext on the other end. It's decrypted with Bob's private key because those 2 public and private keys go together, okay? And then you got the plain text, and that achieves confidentiality. There is the authentication example, and we'll discuss that as we need to. Any questions about this idea? Nope. All right. So today, obviously, these are just boxes and things. So we'll drill down into the specifics of how this works, and I'll go over the algorithm itself today. All right, but I want to just give you some motivations. So asymmetric public key encryption. So it's impossible to overstate the importance of this. Alice and Bob do not need to plan anything ahead of time to communicate securely. They generate their public-private key pairs independently and happily broadcast their public keys to the world at large. I mean, you can literally like go to your Twitter or whatever, and here's my public key and for the world to use. And there's no issues. And then anyone can grab your public key and send you a message, and only you can view it. Do you see the power of that? That's great. So Alice can rest assured that only Bob can decrypt the message she sends. She has encrypted it with, Bob's public. Okay. So he's received the message only he could read, and the message claims to have been sent by Alice, but he has no guarantees that it really did come from Alice, right? So this is the other side of the coin here of RSA. Some public key cryptography algorithms, including the RSA algorithm, have a special property of being commutative, which means that the roles of private versus public key are interchangeable, okay? And so what that means is we can actually achieve authentication also with RSA, right? We don't actually, when you do authentication, you don't just use it as is. You will add on integrity, and that's what becomes a digital signature, right? And that's actually how you do it. But the idea is that now you're just going to flip the keys and you can authenticate, basically. So Alice could encrypt a message with her private key that is decryptable only with her public key. Since everyone knows her public key, you may ask, well, what would be the point, right? Because anybody can look at it, correct? Anybody can look at it. But, well, this message would be readable by anyone, but only Alice could have created it, right? You guys see the value there? Because only her private key produces messages decryptable by her public key. Make sense? So that achieves authentication. So think of an example, for instance, let's say that I'm going to send you an exam, but also your best friend is going to play a prank on you, and they send an exam to you. How do you know that which exam to use? Well, I've made my keys available, right? Then you could check to authenticate which exam came from me. Does that make sense? If I'm using public and private key cryptography. Any questions on this concept? All right. So that's kind of the other side of this. Okay. This provides a form of authentication. So if Alice, and this is actually part of the certificate authorities, right? So this is going to be part of that concept, and digital signatures, as I said. So this provides a form of authentication. So if Alice's plain text message is M, and she first encrypts M with her private key, then with Bob's public key, Bob can take the message he receives and decrypt first with his private key, and then with Alice's public key, and he'll recover M, right? The guarantees are that only Bob can read the message, and only Alice could have sent it. So in one shot here, you're achieving what? What two pillars?
Confidentiality and authenticity.
And authentication, right? Authenticity. Yeah, exactly. Very good, right? So just like before, I think we had done an example where I wanted you to achieve integrity and confidentiality in one shot, remember, via email. Now I could ask you a question where I want you to achieve both confidentiality and authentication in one shot. And you can do that with the RSA framework. Any questions? All right, so let's take a look at this graph. So that kind of summarizes the previous paragraph description. So Alice, right, has a plain text, encrypts with Alice's private key. So that's the authentication part, right? Because only her public key can decrypt it. So that generates cipher 1. Then cipher 1 is encrypted with Bob's public key, right? So that's, it's already a cipher. So then that's going to be converted into cipher 2. Then it is sent over the insecure channel with the internet. It is received on the other end, decrypted with Bob's private key, right? So that's the confidentiality part. Yeah, do you guys agree? And then you get cipher 1, and then cipher 1 is decrypted with Alice's public key authentication, and you get back the plain text message. So it can be read and you've achieved the two pillars, basically. Any questions? All right, so this is an important, I think, like almost like a beautiful thing. You know, it's like amazing, right? That logic is very interesting. All right, so just a few additional history and terminology. So public key encryption structure, publicly proposed by Diffie and Hellman in 1976. All right, so they actually proposed like the idea. So they came up with, okay, if we do these things, which we believe they can be done, you know, we'll have this PKI infrastructure, as it's sometimes called. It's based on mathematical functions, mainly algebra. And we will look at it. Asymmetric uses two separate keys, public key and private key. Public key is made public for others to use, and some form of protocol is needed for the distribution, right? So this was just like a call, you know, to people to develop it, and then it was answered by several teams. I believe the team at MIT or something created the best one. All right. So public key infrastructure, so there's the graph. Basically, as you can see, there's way more files involved, and this is what I was saying. You know, whenever I do this class, I've noticed there's quite a bit of confusion in the files and things. Work with a partner. Okay, label things very well. All right, because it gets a little bit tricky. Or not, I don't know. Okay. All right, so basically, let's take a look. This is directed toward providing confidentiality. You have a plain text input X, let's call it. There is, of course, an encryption algorithm, which is based on just, you know, algebra functions, RSA in this case. Okay. So this is going to Alice. Yeah, from Bob to Alice, encryption with public key. So Bob then needs to have, it's got basically like a key, you know, a key ring, right, of a whole bunch of public keys, you know, friends, etc. So it's got Alice's, so it's gonna, Bob will grab Alice's public key, and then using the RSA algorithm, encrypt it. Now remember, this is not meant to be used for messages. This is really just for exchanging the secret key of AES or DES, right? But I guess you could send messages too. I mean, it's not impossible. It's just not geared for, made for it. So then you have Alice on the other end. Alice will receive the message, and then she will use her private key to decrypt the message. And that's it. Okay. Because she has her private key and she has kept it, you know, she doesn't share it with anyone. Okay. So these are all the elements involved: the plain text, readable message or data that is fed into the algorithm as input, the encryption algorithm that performs the transformations on the plain text, public and private key, the pairs, the ciphertext, which is the scrambled message, produces output, and then there's the decryption key. Okay, so those are the elements. Okay, so this one would be the graph directed toward providing authentication. Okay, so here we have a plain text message. It's once again going from Bob to Alice. Okay, so here Bob is going to use his private key, right, to encrypt the message with RSA, produce the ciphertext, and then it's going to send it's going to send it. The decryption algorithm then, Alice will use the decryption algorithm because it was generated with Bob's private key. Alice will use Bob's public key to decrypt it, and so she'll be able to decrypt it. Now, in reality, it doesn't quite work like this. You have to actually add integrity to this, because otherwise, I mean, you would be getting thousands of plain text after the decryption, and how would you know which one is the true one, right? Because, I mean, they would all be letters. So really, you would have to read all of them and kind of say, oh, this is the one that's written in English and makes sense, versus a whole bunch of other ones, which may look like English, but don't make sense. So that to avoid that, you first calculate a hash, and really the hash is the thing that gets gets the encryption. Does that make sense? But we'll take a look at that a little bit later when we do the more advanced procedures. All right, so user encrypts data using his or her own private key. Anyone who knows the corresponding public key will be able to decrypt the message. So that's the basic overall logic of this, the so-called RSA or asymmetric encryption being commutative. All right, so let's look at some nice statistics or information. So basically there's a few asymmetric approaches or public key crypto systems, RSA, of course, Diffie-Hellman, which we will not cover in the class, elliptic curves, which is, kind of it basically is a technique that is like RSA, but it uses that area of mathematics to basically pick starting numbers. Okay, that's really what it is. If you notice, the best one there, the one that can be used for digital signatures, symmetric key distribution, and encryption of secret keys is RSA, and then elliptic curves are also, like a RSA plus some additional techniques. Okay, but in general, the framework is very, very similar. But in this class, we will only focus on RSA. Okay. Now, in the past, students have done, for instance, elliptic curve as a research project. So remember that at the end of the semester, 10% of your grade is your project. So it's not a lot of points, and it can be like a research project that you do. As long as you implement in either code or like OpenSSL type of Linux applications, it's fine. So you do an explanation, for instance, of elliptic curve, and then a demo of how you do it, for instance. Or you write the code if you want. That'd be great. But anyway, that's just, an example of what the term project could be at the end of the semester. All right. All right. So some requirements for public key crypto systems. Okay. Computationally easy to create key pairs. This is important, right? So computationally easy to create key pairs. It shouldn't take that long. As you will see, it won't. What's important is they need to be very big, all right? I'll show you, for instance, that if you create keys that are very small, you can break them. You can easily break them with like FactorDB. So it's literally like a website. And you enter something and you'll see that we can break it. So the trick is that the values need to be big in order for them to be very hard to break. Computationally easy for sender, knowing public key to encrypt messages. Okay. Computationally easy for receiver, knowing private key to decrypt ciphertext. Now, this is important. Computationally infeasible for opponent to determine private key from public key. Because remember, the public and the private key are related, right? And you're making the public key available. So, you might start to think, okay, if I have the public key, can I get the private key? And that's really the whole trick in breaking RSA is how would you be able to do that? So it's the fun of it. All right. So no one has been able to do it for really large numbers. For small ones, I'll show you in this module. Also computationally infeasible for opponent to otherwise recover original message. And useful if either key can be used for each role. So useful if either key can be, the commutative thing. All right. So a little bit now. So the asymmetric, don't forget the asymmetric framework is just like the idea. And then RSA is the specific solution that was found. As you see there, RSA stands for Rivas, Shamir, and Edelman. Those are the three scientists that put together RSA. So developed around 1977. That's a long time, right? So 40 years, almost 50 years. And, this framework has been going strong, hasn't been broken. Most widely accepted and implemented approach to public key encryption. And then there's elliptic curve cryptography, which, like I said, is like the research security like RSA, but with much smaller keys. So it tries to address the issue that the keys in RSA definitely need to be bigger and bigger and bigger and bigger as computers get more and more powerful, right? Think about it. So that's where the whole quantum computer thing comes in, right? Quantum computer is supposed to be like a supercomputer. And so then the quantum computer would be able to try potentially all the possible combinations and find the right key, the right set of keys, okay? And break RSA. So as computers get more powerful today, the solution is just to make the keys bigger. And we'll play with that in several of the lab assignments. And so as computers get more powerful, keys get bigger. So what if computers got so powerful like quantum computers that, it doesn't matter how big they are, they're going to be broken. All right, so anyway, that's some additional ideas. Is that the end? Okay, yeah, so that seems to be the end of these slides. Okay, all right, and then I have another set of slides. It's very short, so I think, let me just double check that the Zoom is still working. It's still recording. I think the share is what keeps breaking. It might be related to my PowerPoint. Okay. All right, so let me pause the recording maybe.